Okay. So am I audible, Professor Hota?
Yes, yes.
Yeah.
Right. So, good afternoon. I am Shobik. I am a second year PhD student at Systems and Control Engineering, IIT Bombay. I welcome you all to the last talk of this eventful year organized by SysConTalks in association with the Interdisciplinary Program in Industrial Engineering and Operation Research at IIT Bombay. We at SysCon organize frequent academic activities like student faculty talks and invited sessions from eminent personalities from different universities and academics. Today, we are pleased to have Professor Ashish Ranjan Hota with us. He is an assistant professor with the Department of Electrical Engineering at IIT Kharagpur. He was a postdoc researcher at Automatic Control Laboratory, ETH Zurich in 2018 and received his PhD from Purdue University in 2017. Moreover, he has completed his BTech and MTech from IIT Kharagpur in 2012. He is a recipient of several awards like Outstanding Graduate Research Award from the College of Engineering, Purdue University, and the Institute Silver Medal from IIT Kharagpur. His research interests are in the areas of game theory and behavioral decision theory, stochastic optimization, control and learning, and resilience and security of network system. On behalf of the entire IITB community, I welcome you, Professor Hota. So today he is going to speak on the impacts of game theoretic activation on epidemic spread over dynamical network. I welcome you again, Professor, and without further ado, I would like to pass on the stage to you. Thank you.
Okay, thank you, Shobik. Thank you very much for the invitation and the opportunity to speak in front of you. Very, very happy to be among all of you virtually. Uh, so, uh, I have in the full screen mode. So, if you want to ask anything, please stop me because I may not be able to see the chat window. So, and let this be very informal. So, whenever there is any question, please just stop me. Okay. So shall I start now?
Yes, Professor, you may start.
Okay. So today I will talk about some of the work that we are doing recently on game theoretic models on epidemic spread over dynamical or time varying networks. So this is joint work with two of my students, Tanya and Kavish. So as we know, infectious diseases spread through society by exploiting interaction between people. There have been a lot of work on mathematical modeling of epidemic evolution. So particularly the problem that we are facing today with regard to COVID is that in the absence of effective treatments and vaccines, it is very important to understand how people interact during the epidemic evolution, because that will tell us how the epidemic is going to evolve in future and maybe take precautionary measures. So in this work, we look at one aspect of this, specifically how humans tend to choose their level of interaction during the spread of the epidemic. And we study this in a framework of activity-driven networks, which I find very, very nice, as we are going to see soon. So let me first introduce the model, and then I'm going to describe what are the problems that we try to answer and what are our results. So the model we study is the following. So let there be n nodes denoted by V1, V2 up to Vn. So these represent individuals, basically human beings. So each node can remain in various possible epidemic states. So in the first model, we look at the case where each node remains in one of four possible states: susceptible, asymptomatic, symptomatic, and recovered. So we treat both asymptomatic and symptomatic states as infected states, and not only infected, they are also infectious. So a node which is either asymptomatic or symptomatic can potentially cause new infections. Now, how do the states evolve? Now, the states evolve in the following way. So we look at a discrete time model. So if at time k, node Vi is susceptible, then we denote it by Vik belonging to state S and so on. So susceptible we denote by S, asymptomatic by X, symptomatic by Y, and recovered by R. Now, given a network or contact pattern between the nodes, the nodal states evolve as follows. So if a node Vi at time k is susceptible, then at the next time it is asymptomatic with probability beta x for each asymptomatic neighbor and with probability beta y for each symptomatic neighbor. So both asymptomatic and symptomatic neighbors can cause node Vi to become infected, but probably with different rates. And upon infection, the nodes initially become asymptomatic. Now, if the node is asymptomatic at time k, then at time k plus 1, it can either recover straight away with probability delta x, or if it does not recover, then it can become symptomatic with probability nu times 1 minus delta x. So if it does not recover, then with probability nu, it becomes symptomatic. Now, if a node is symptomatic, then the only way for it is to become recovered, and that happens with probability delta y. So this describes the evolution of nodal states given a network or contact pattern. Now, this model is this is not the most popular model as far as epidemics are concerned, but there are two more popular models. One where this asymptomatic stage is called the exposed state. So in the classical, in the literature, this is known as the SEIR epidemic model, where the exposed state does not cause any new infections. And that we can recover by setting beta x equal to 0 and delta x equal to 0. Similarly, in the more conventional SIR epidemic model, there is only one infected state. So there are only 3 states: susceptible, infected, and recovered. And we can also recover the SIR model by setting the transition rate nu to be 0 and assuming that none of the nodes are initially symptomatic. So only X is the only infected state. So far, I have specified the evolution of nodal states given a network or contact pattern. I have not said anything about how the network is formed, which we describe now. So the network is time varying, and it gets defined in the following way. Now, for each node Vi, we denote by pi z comma I k as its activation probability at time k if it is in state z, which can be one of the 4 states that we just described. Now, at the initial time, each node is in one of the 4 possible states. Now, at each discrete time k, the node Vi activates with probability pi z comma I k, where z is the state of that particular node at that particular time. Once the node activates, it chooses di other nodes randomly and uniformly among all nodes and forms edges with them. So di is the degree of node Vi, and different nodes can have different degrees, but the degree of the node is fixed. So the degree does not change with time, basically. Now, once these edges are formed, the nodal states get updated as I described earlier. So once these edges are formed, this describes the network at time k. And then the nodal states get updated. And once the states are updated, the edges are discarded. And we start again from the empty network, and where nodes again decide to activate with certain probability, form edges, and so on. So this process repeats itself. And one thing to note here is that I have not assumed anything about the activation probabilities. So in this form, the activation probability of a node depends on its state. It can be different for different nodes. For a given node, it can be different if the node is in different states, and it can also be different at different time instances. So it's sort of completely general at this point. Any questions so far?
Hi Ashish, what is meant by degree of a node?
So it is the number of neighbors that a node chooses to connect with. So let me give an illustration. So let's say we have four nodes, 1, 2, 3, 4, and 1, 2, and 4 are susceptible. That is, they have not been infected so far. And node 3 is, let's say, infected and symptomatic. So let's say at this point of time, two nodes activate. That is, let's suppose that nodes 1 and 3 decide to activate themselves. And let's say the degree of node 1 is equal to 2, and the degree of node 3 is equal to 1. And then upon activation, node 1 chooses two nodes to connect with because it has degree 2. Similarly, node 3 chooses one node to connect with because it has degree 1. So in this case, we assume that suppose node 1 chooses 2 and 4, and node 3 chooses 4, and these are the connections that get formed. So does that answer your question?
Yes, thanks.
Yes. Okay. And these are the edges that are formed, and then the nodal states may get updated. So here, once the edges are formed, we remove the direction. So it's an undirected edge. And node 2 only has only neighbor of node 2 is 1, which is healthy. So node 2 cannot become infected. Node 1 has two neighbors, 2 and 4, which are both healthy. So it also cannot become infected. And 4 is the only node which has two neighbors, 1 and 3, and 3 happens to be infected. So it is possible that node 4 becomes infected. And upon infection, it initially becomes asymptomatic. So that is what happens here. So at the end of this time period, 1 and 2 remain healthy, 3 continues to remain symptomatic, and 4 becomes asymptomatic infected. Now, at the next time, we again delete these edges. And in the next time, let's say two other nodes activate, 2 and 4. Let's say that degree of node 2 is 1, degree of node 4 is 2. And let's say they form edges in this way. So 4 chooses 1 and 2, 2 chooses 4. So there is only one edge now. And in the next time instant, it is possible that 2 becomes infected. So upon initial infection, it becomes asymptomatic. And then 3 and 4 can recover. So we allow asymptomatic infections to recover directly. So this is how the epidemic process evolves. So any questions so far? Okay, I take that as a no. So let us proceed. So in this talk, we will discuss some of the results in the following context. So we derive individual-based and degree-based mean field approximations of the process I just described. Then we present a game theoretic formulation where nodes choose their activation probabilities in a selfish and decentralized manner. So nodes decide whether they should activate themselves or not, and with what probability they should activate themselves. And then we present some numerical results, which shows the impacts of bounded rationality when nodes are not perfectly rational, the impacts of asymptomatic carriers, and the impacts of degree distributions of the nodes. And if time permits, I will also describe some of these results in the context of SIS epidemic, where nodes upon recovery can potentially become reinfected again and again. Okay, so moving forward. So then how do we study the evolution of the epidemic states and the networks in this particular model? So one thing we can do is that each node can be in 4 possible states. So the exact Markovian evolution has a very large number of states, 4 to the power n. So in these type of epidemic models, most of the prior work have relied on mean field approximations, where they keep track of the probability of each node being in different epidemic states. So in particular, we can capture this by introducing indicator random variables. So we say that SIK is the random variable that keeps track of whether node Vi at time k is susceptible or not. And similarly, xik, yik, and rik for asymptomatic, symptomatic, and recovered states. And then the probability of the node vi being susceptible is the expectation of this indicator random variable, which we denote by small sik. And we try to write like simple ODEs which capture the evolution of this, at least approximately the evolution of this quantity. So before we do that, let me introduce some ugly looking notation. Apologies for that, but there's no other simpler way of writing it. So let's say di be the degree of the node, and then we write di bar as di divided by n minus 1, where n is the total number of all nodes. We first introduced two quantities, beta ij xk and beta ij yk. So beta ij xk is a product of two terms. One is beta x, which is the probability with which infection sort of transmits from an asymptomatically infected neighbor. And the second term here is essentially the probability that there is an edge between nodes vi and vj when conditioned on the fact that node vi is susceptible and node vj is asymptomatic. So this is if you recall, the edge formation can occur in two ways. The susceptible node I activates and then chooses node j as neighbor, or the asymptomatic node j activates and chooses node vi as neighbor. And since we have to take union of both of these events, so that introduces this 1 minus of like 1 minus of complement, product of complement of the edge not being there. So that's what is causing this. And similarly, beta ijy k is the product of beta y, which is the rate at which infection passes on from a symptomatic neighbor. And then the next term here is the probability that there is an edge between vi and vj, where vi is susceptible and vj is symptomatic. So once we define these two, and then we have the following result on the evolution of the probability of node I being in different states. So if node I is susceptible at time k, the probability of node vi being susceptible at time k plus 1 relates to the probability of node vi susceptible at time k as follows. So either it is susceptible now, and then this term here captures the rate at which susceptible nodes become asymptomatic. So they can become asymptomatic if they come in contact with either asymptomatic or symptomatic neighbors. So the probability that node, and this is the sum over all other nodes, the probability of becoming infected from node j times the probability that node j itself is asymptomatic infected, and then similar term for the symptomatic case. And the rest of the terms are fairly straightforward if you just evaluate the expectation of the indicator random variables. So any questions at this point?
So do you assume this pi ij, those constants, pi z I, that you assume that a sequence is given to you and you are doing the ODE analysis for a given sequence of it, or
Yes. These quantities are known. So if these are the so assuming that these are known in a way, then this is how the mean field evolves. So later on, we're going to see when we allow nodes to choose these themselves, and then what form does it take?
Yeah. Right now, you are assuming it's a given sequence and you are doing the ODE analysis, right?
Yes, correct.
Hello, Ashish.
Yes.
This 3-point A, 3-point and 3-point B have some approximations. That is your notation, or I didn't get this?
Yes, these are not equal. These are approximations. Essentially, we take two approximations. One is, I think, so in one place there is a product term. So we have to take probability of two events which are in a product form. They are not really independent, but we assume that they are independent.
So actually, coming from ODE approximation, right? You're using the mean field.
Yes, so I simply write down the exact Markovian evolution and then try to evaluate the expectation. And
Yeah,
in some, right, and in some cases, it sort of, there are certain product terms which are of two events which are not independent, but I assume that they are independent, and then which would be more or less true in a very large network, and then that gives rise to this. So it's not equal in a way.
So you take this in the limit n tending to infinity, right? The n is the number of nodes. I mean, I don't know what you called it.
Right. At this point, it's not very precise. We don't give a rate at which, we don't give statements that if the number of nodes is high enough, then this is true with high probability. We don't give a statement like that. We sort of assume that under the assumption that these are independent, this should be the equation, how it
You're
looks.
just assuming independence and you're deriving some.
Right. Yes. I mean, it would be true, but it just we probably have to do it. Maybe bit of a messy calculations will be involved, but more. I'm very confident that it will be true in the last
mean field approximations. You take the mean, this one n tending to infinity, and
right. Yeah. Okay. Any further questions? Okay, then let us move ahead. So this was all very nice, but we, sometimes it's also in very large network, a further approximation is used, which is called the degree-based mean field approximation. And in this case, it is assumed that all nodes with a given degree are sort of statistically equivalent in some sense. And for the proposed model, we now state the degree-based mean field approximation. First, let us introduce some notation. So let calligraphic D be the set of degrees of the nodes. So it's 1 to up to D max, where D max is the node with the maximum degree of all the nodes. Let MD be the proportion of nodes with degree D. So it's like out of all the nodes, what fraction has degree D. So it's like the empirical degree distribution, like the histogram of the degrees of the nodes, normalized. And in this case, the state variables represent the proportion of degree D nodes that are susceptible, asymptomatic, symptomatic, or recovered at time k. And these are denoted by S sub dk, xdk, ydk, and rdk. And we assume that all the nodes with degree D in state Z choose an identical activation probability denoted by pi d comma z at time k. And as before, we denote these effective infection rates, beta x dt and beta y dt. So before it was between two nodes, beta x ij, between nodes bi and bj. Now it is between 2 degrees. So this is the rate at which a degree D node can potentially become infected when it comes in contact with an infected degree T node. So these are these two analogous quantities. And this is how the degree-based mean field approximation is defined. So this is not a derivation in any way. This is just assuming that all nodes with a given degree behave in the same way, are equally likely to be in different epidemic states. This is how the states are going to evolve. So it's not a mathematically precise statement, but there's an assumption, but seems to work well, or seems to capture the true epidemic evolution in large enough networks.
Yeah, so I think this is good. As you said, it is approximately good in large networks, right?
Right. Okay, I mean the precise, like the symbolic notation is not important, but I think what will be more important is to see how we then rely upon this to study our game theoretic model, so we can get to that. So as I said, so far we have assumed that the activation probabilities are exogenous, so no one is deciding them; they are somehow coming to us. But let's move ahead. Okay, so here is the game theoretic formulation. So at each time instant k, each node myopically decides between two possible actions. So either it can activate and go out, form connections, or it cannot activate and stay home and do nothing. Now, all nodes with a given degree and epidemic state face an identical decision problem because we are re-awareing the network all the time. So we assume that all degree D nodes adopt the same strategy. Now, nodes with degree D form a subpopulation with degree D. To be clear what I mean by that. Now, the strategy of a node with degree D in epidemic state Z is denoted by pi D comma Z. And the strategy profile of all the nodes is basically the collection of all the pi's. Okay, so this is like the strategy profile of the entire population. Now, we need to define the utility functions in order to reason about a game theoretic model, right? Now, let's say at time k, a strategy profile pi is given to us. And the nodes are also aware of some information about the global epidemic state, denoted by E bar of k, which we'll make precise very soon. Now, if a node activates, it receives a benefit of 1. So it's benefit of socially interacting with others. And if it does, if it does not activate, it does not get that benefit 1. Now, and if a node is infected, it also incurs a loss, capital L. Now, for a susceptible node with degree D, we define its utility as follows. So if this degree D and susceptible node activates, then it gets the benefit of 1. But there is a risk of becoming infected, let's say. And if it becomes infected, then it encounters a loss L. So that quantity together is L times RD, where RD is the risk factor, which I will specify very soon. And if it does not activate, then the utility is that minus L times the risk factor if it does not activate. So even if a node does not activate, someone else can activate and form a connection with it. So the node has no way of preventing it. Therefore, the risk is not 0, but obviously it will be much smaller than when the node activates and actively seeks out other nodes to connect with. Okay. So this is what happens with susceptible nodes. Now, if a node is asymptomatic, we assume that they are not exhibiting symptoms, so that we assume that they don't know that they are infected, and they behave and they continue to behave as susceptible nodes. So we define their utilities as the same as that of the susceptible nodes, if they have the same degree and if they choose the same action. Now, if a node is symptomatic and then it knows that it falls sick, so it knows that it is infected, then the utility is defined as follows. So if there is no further risk of infection because it is already infected. So in the known infected state, if it activates, it gets benefit 1. If it does not activate, it pays some penalty. So penalty for violating quarantine norms. So you can view it like that. And if it does not activate, then it doesn't get any benefit, doesn't pay any price. And finally, if a node is recovered, and then everything is great. So if it activates, it gets benefit 1. If it does not activate, it gets benefits 0. Okay.
Ashish, Hemachandra again, the C is a positive fraction or something?
C is a positive number, yes.
Number or a fraction? It can be
a real number, it can be anything.
Oh, okay.
Yeah. C can be larger than 1, yes.
So what is the meaning of negative utility then? A sort of residuality, what is it capturing?
So C basically is like government tells you don't go out if you are COVID positive, but if you still go out, then you have to pay a very heavy fine. So C essentially captures that.
Okay.
Or you can also view it as a reward. So if you are a known positive patient, then government says, okay, we'll pay you say 500 rupees per day, but don't go out. So you can view it like that. So in that case, the utility upon activation will be 1, but utility upon not activation will be C. And C can be larger than 1.
Okay, I see.
Yeah.
Okay, yeah.
Okay, so far, so then we now have to think about what will a node do. So we can say that, okay, there are two possible actions. So we just compare the utilities and then pick the one which gives us the higher utility all the time. But then that will lead to a very binary type of decision. So we try to make it more interesting, even more notation heavy. So there is a very popular choice model called the logit choice model, which says that when you have to pick between multiple discrete actions, you pick the one that gives you higher utility with higher probability. So you may pick the options that give you lower utility, but with lower probability, and this sort of allows that. So more precisely, a node with degree D in epidemic state Z chooses to activate with this probability on the left-hand side, which is basically e power lambda times the utility upon activation divided by e power lambda times utility upon activation plus e power lambda times utility when it does not activate. And as you notice, what essentially determines this activation probability is the difference of the utilities, not the absolute utilities, where the difference delta U is defined as utility upon activation minus utility if you do not activate. So this left-hand side we can view as some sort of a best response of a node with degree D to the global strategy profile pi. Now the parameter lambda captures what is some sort of bounded rationality. If lambda equal to 0, then activation probability is 0.5, regardless of anything that the utilities are telling us. If lambda goes to infinity, then nodes activate with probability 1 if utility upon activation is larger than utility if you do not activate. Okay, so it's like a setting where nodes are perfectly rational, or like people play their best response, pure strategy best response, so to speak. And for intermediate values of lambda, nodes pick the action that gives them higher utility with a higher probability, or nodes pick the action that gives you higher utility more often. If we consider a setting where there are many nodes and then they take these decisions repeatedly. Any questions at this point? Okay. And now we define the notion of equilibrium that we study here. So this is called quantal response equilibrium with parameter lambda. And it's basically defined as a consistency condition, right? So at the strategy profile, a strategy profile is an equilibrium if all nodes of all degrees and in all states, the probability with which they choose to activate coincides with the corresponding activation probability in this strategy profile. Okay. So at the equilibrium, the probability with which a node activates under the logit choice model coincides with the equilibrium strategy. This is a known result, if there are a finite number of subpopulations and each subpopulation encounters a finite number of actions to choose from, then there always exists a quantal response equilibrium. Okay. Any questions at this point? So one assumption is that this parameter lambda is same for everybody. So it's not that some degrees have a smaller lambda, some other degrees have a larger lambda. That's not the case. Everybody has the same lambda, so to speak. Okay, so let me move ahead. So remember, what is important here is the difference in the utilities, and I have not yet specified that for the case of susceptible and asymptomatic nodes. So here we make it precise. So this risk factor I told you about. So we define it as the probability of a node becoming infected, given that it is currently susceptible and it activates itself. And then this is the first risk factor. And the second one is that the probability with which the node becomes infected, if it is susceptible, and if it does not activate itself, and under the global strategy profile pi. And we have this lemma here, which basically says that, I mean, we basically calculate the right hand side conditional probabilities in more detail, but we have in the regime where the maximum degree is very small than the number of nodes, the difference in the utilities reduces to a sort of very simple form, approximately. Essentially what happens is that the delta U is 1 minus LD times beta x bar k plus beta y bar k, where x bar k is the expected fraction of all nodes that are asymptomatic at time k, and y bar k is the expected fraction of all nodes that are symptomatic at time k. So to calculate the difference in utilities and therefore to determine their activation probabilities, nodes do not need to know the strategies of other nodes, and they also do not need to know what percentage of degree 1 nodes are infected, what percentage of degree 2 nodes are infected. Only knowing the aggregate quantities suffice. At least is approximately gives them the difference in utility that they are looking for. And once we characterize that, then we can simply write down what are the activation probabilities at the quantal response equilibrium with parameter lambda. So for both susceptible and asymptomatic nodes, it depends on e power lambda minus e power lambda times the difference in utilities. So I've just substituted this expression in equation 5 here. And for symptomatic and recovered nodes, we know the utilities which don't depend on the current epidemic state and so on. And then we can just simply write down what are the corresponding expressions. Okay. So essentially, you can view these activation probabilities as some sort of a feedback law, which uses feedback as the current epidemic prevalence, x bar k and y bar k. Okay. And as intuition suggests, if node degree is higher or the amount of loss is higher and the epidemic is highly prevalent, then the activation probabilities become smaller. So when there is more, if I'm connecting with more people, then I should be more careful. If the loss of an infection is very high, if there is a lot of epidemic prevalence going on right now, then I should reduce my activation probability. And naturally, if I have already recovered, I don't care what is the current epidemic state. I activate with high probability anyway. Any questions at this point?
Yeah, Ashish, Hemachandra again. Just curious if lambda is equal to 1 will mean something or?
No. Lambda equal to 0 means all the activation probability is 0.5. Lambda equal to infinity means you pick with probability 1, like this pi becomes binary. But lambda equal to 1 does not have any specific.
Okay. Oh, I see.
Yeah. Because if lambda is 0, then e power lambda is 1.
Yeah, that is correct. That I think is okay. Yeah.
Okay. Any other questions? Okay. Now let us move ahead. Now, as I discussed, the very popular SIR model is a special case of this. We can also look at what the activation probabilities look like in that case. So there is no Y state here. So there is only susceptible, infected, and recovered. And therefore, we set the Y bar k equal to 0, and then by doing that, we can write down what are the activation probabilities of the equilibrium. Okay, but let's go to some numerical results, which will make certain, the implications more clearer. So first we look at the SIR epidemic, and then first we study the impact of bounded rationality. So in the first case, we consider that all nodes have the same degree. So the nodes are homogeneous as far as their degrees are concerned. And so we simulated and let's say there are 100 nodes. So we simulated the exact epidemic evolution on 100 nodes. And we also looked at the degree-based mean field approximation, which is like a scalar equation in this case, because there is all nodes have the same degree. There is only one subpopulation. And then they tend to match closely with each other in most of the cases. Now, the figures on the left column correspond to the case when lambda equal to 0. So in this case, the activation probabilities are always 0.5. And we see that there's a very sharp increase in the proportion of infected nodes, denoted by the red curve in the top figure here. Very sharply it increases and goes down. And then the proportion of recovered nodes also increases and it becomes 1 very quickly. Then we look at the case, then we sort of increase lambda, and we want to see what happens when nodes become more and more rational, so to speak. So when lambda equal to 1, we tend to see that and in this case, the parameter C, penalty parameter is 4, which is bigger than 1, right? So the nodes who are recovered activate with high enough probability, something around 0.8, as seen here. And nodes who are infected activate with low probability. And nodes who are susceptible, their activation probability sort of depends on the current epidemic prevalence, right? So if you see here, the last two quantities are constant, don't depend on the current epidemic state. But the activation probability of susceptible nodes depends very much on the current epidemic prevalence, and that is what we see here. So initially, when the epidemic was on the rise, so people reduced their activation probabilities. And then eventually, when the epidemic subsided, people sort of increased their activation probabilities. Now, when we increase lambda further, so lambda 10, we almost see like a very rational type of agents. So in that case, the activation probability for recovered nodes is like very much 1. Activation probabilities for infected nodes is 0, but then for susceptible nodes, they do activate with intermediate levels of probabilities. But more interestingly, this red line here, which captures the proportion of infected nodes, is pretty much flat for a long time. So people, if you leave them to take their own decisions, and then they tend to flatten the curve on their own, at least as far as this model is concerned. Now, can you guess why we are seeing this sort of very nice flattening? Something very interesting is taking place, and if the answer is there in the next slide, but if anyone can guess. Okay, so here is why. So remember, the difference in utilities in this case, essentially, we had this type of a formula. So if the exponent, so there are two cases, one where the exponent is less than 0, and one where the exponent is bigger than 0. So if the exponent is bigger than 0, then we activate with probability greater than 0.5. So that defines a threshold on x bar. So if x bar k is less than 1 by L d beta x, then we activate with probability more than 0.5. Otherwise, we do not activate very frequently. So the left side plot essentially shows that how the activation probability as a function of x bar, and how does it look like for different lambda. So when lambda equal to 0, it is flat at 0.5. But for lambda equal to 10, then there is a very sharp transition. So when the activation probability is just below the threshold, you tend to activate almost with probability 1. Otherwise, you activate with probability very close to 0, so to speak. Now, what that reflects is the following. Now, if x bar is slightly larger than the threshold, then you drop your activation probabilities, and that tends to decrease x bar. But when x bar decreases slightly below the threshold, then people tend to activate again, and then that tends to push x bar up. So this leads to like very sustained type of oscillation in the activation probabilities, and then everything that is not 0 or 1 essentially uh, is surrounded around the vicinity of this threshold. So all these activation probabilities that we're looking at, say 0.2, 0.3, 0.5, it doesn't matter. Since it is between 0 and 1, X bar must be very close to this threshold. And that is exactly what we see in the last curve here. So what happens is that any decrease in X bar is counteracted by an increase in activation probability and vice versa. Okay. Any questions here? Okay, I shall move ahead. So next we look at the impact of asymptomatic carriers. So we consider two cases, one where we know the true epidemic prevalence, like what percentage of infection is actually asymptomatic. And the second case where nodes don't know, I mean, we are only testing symptomatic cases, so people only know what is the prevalence of symptomatic infection. So these two regimes we compare here. The figures on the left panel are when this quantity nu, which is the rate at which asymptomatic nodes become symptomatic, is 0.01. That is very small. That means that asymptomatic nodes don't become symptomatic very often and largely recover without ever becoming symptomatic. And in that case, we see that there's a very large sort of proportion of nodes which are asymptomatic, but if it doesn't get detected, that can lead to nodes activating with very high probability. And the second regime is when nu is 0.9, that is asymptomatic nodes almost always and very quickly become symptomatic. In that case, most of the infections are actually of the symptomatic type. So the asymptomatic is denoted by the red line and symptomatic is denoted by the yellow line here. And the last curve shows that when nodes are quickly becoming symptomatic, then there's not much difference in the activation probabilities because most of the infection is symptomatic anyway. So even if you don't know many, like the asymptomatic proportion, that doesn't change your activation probability very much.
Hello. Can you hear me?
The degree distribution is not. Yeah, there was a question. Yes.
Yeah. So actually, I forgot. You said that asymptomatic people would not be knowing, and so their actions would be similar to the susceptible people, right?
Yes.
But their utilities are also similar. I don't remember.
They don't know, so they incorrectly think that they are susceptible.
Yeah, right. But utilities that they gain should be different, no? Because they cannot get infected again. So they will not occur that minus L, right?
No. So at the time of activation, they will actually not occur it. But at the time of deciding whether I should go out or not, they don't know that they are infected. So they think that, okay, I am still susceptible. So let me be careful.
They assume their utility to be something else, but in reality, their utility is something else. So, but that aspect is not coming into the analysis, right?
Because we have not analyzed it. We have analyzed it assuming that they behave as if they are susceptible.
But yeah, I mean, I don't know. Maybe in the future work, you can think about how to consider. I think considering this aspect might make some interesting lead to some interesting stuff there.
Yes, I mean, absolutely.
Right now, I'm not able to think, but I think it might have. I mean, because the thing is like they're going to choose, right? The actions again. So something has to be there which will make an impact on that, right?
Right. Yeah. I mean that is something. That's a very good point. But we have not studied it at this point. We could also think of how to do it. But but certainly something to be.
Yeah, think about how to incorporate that. Maybe like.
Yeah. Absolutely. Yeah. Okay. So finally, we look at the case when the node degrees are heterogeneous. So we consider three cases. One is the homogeneous case when all nodes have the same degree. Then we look at two-degree distributions, binomial and power law distribution. So it's sort of popular in network science. I think binomial distribution occur in Edo-Sternly graphs, and power law distributions take place in the preferential attachment type models. So we choose these distributions such that the mean degree is the same for all three cases, 5 in this case. So naturally, the activation probability is now a function of the degree as well. So different degrees, nodes of different degrees in the same epidemic state have different activation probabilities, which we see in the first figure here. So for nodes with very low degree, the activation probability doesn't decrease very much, even when the infection prevalence is very large. But when nodes have a very high degree, then activation probability sort of drops as a function of infection prevalence at a certain threshold. Now, if you compare like the proportion of infected in both asymptomatic and symptomatic infected in all three cases, we tend to see that the homogeneous and binomial degree distributions have a similar sort of profile. But for power law distributions, the peak of infection is sharper, both in the red line as well as in the yellow line. So that's essentially, one factor is that in the power law distribution case, a large fraction of nodes have a very small degree, and they continue to activate at a high rate. So they do not decrease their activation probability by much, and that contributes to a higher peak. So how are we doing with respect to time? So we have some results on the SIS case as well, but if we are running out of time, we can also I can shorten the discussion of that section.
Yeah, Professor, you can take maybe 10 more minutes.
Okay.
That is okay. Yeah.
Okay, thank you. So then we look at the case of any questions so far about the previous segment. Yeah. Should I continue? Hello?
Yeah, Ashish.
Yes, you are visible. I mean, you can share your screen. Professor, could you please unmute yourself because it seems that you've muted.
Sorry.
Yeah.
Am I audible now?
Yes, you are audible.
Okay. I think also Manjunath asked a question.
No. I was just saying continue. I thought there was some this thing there, and I said maybe you should just continue.
Okay.
Nobody was answering, so I just volunteered an answer.
Okay, thanks a lot. Okay, so let us indeed continue. So the SIS epidemic is more simpler. There are only two possible epidemic states, susceptible and infected. There is only one rate at which susceptible nodes become infected, and then infected nodes recover and become susceptible. We look at a very analogous network formation process. So each time nodes activate with a certain probability, which depends on their state. And upon activation, they choose a certain number of neighbors to connect with. Once the network is formed, then if a node is susceptible, then it becomes infected with probability beta for each infected neighbor. And then If it is infected, it recovers with probability delta, and so on. Once again, we derive the individual and degree-based mean field approximations. So the degree-based mean field approximation essentially is defined in this way. Again, very analogous notation. So I don't want to spend much time here. Utilities are once again defined in a very similar way. For susceptible nodes, it is 1 minus L times the risk factor, which is the probability that the node becomes infected at the next time step. If it does not activate, it is minus L times the probability with which it becomes infected. If it is already infected, the utility is 1 minus C if it activates, and 0 if it does not activate. The equilibrium activation probability is once again very analogous expressions, exactly the same.
Professor Ashish?
Yeah.
Yeah, there is actually a question. May I read it?
Yeah, please.
Yeah, so Pradyumna is asking, in the model, the degrees of the nodes was changing with time?
No, it was not. It was not. Degree is same. Degree is fixed.
Okay. So he continues that when you assume the homogeneous degree distribution, does that mean nodes have the same degree all the time?
Yes, nodes have the same degree all the time. Degrees don't change, and all nodes have the same degree at all times.
Okay.
Okay. Yeah. Now, once we have these expressions for the activation probabilities at different times, which depends on the current epidemic state, we can substitute it in the DBMF approximation that gives rise to a closed loop dynamics, so to speak. It's a very nonlinear dynamics, but we sort of, let me highlight what happens in a very particular case. So let's consider the regime where the parameter lambda equal to infinity, that is, nodes are perfectly rational. They activate with probability 1 if utility of an activation is strictly larger than the utility if they do not activate. Then we assume that the parameter C is bigger than 1. That means if a node is infected, then its activation probability is 0. And then we also consider the fact that all nodes have degree D. That is, the degree distribution histogram is like it's a delta, like a degenerate point mass, so to speak. So in this case, the DBMF approximation state variable is just a scalar because all nodes have the same degree. So this is just a scalar. And this figure essentially shows that what happens to this. So there are, we look at sort of 3 different subcases. The first case is when the recovery rate delta is bigger than beta times D. So in this case, so here is what happens, right? So the activation probability for susceptible nodes in the regime where lambda goes to infinity is either 1 or 0. And it is 0 when this quantity is negative. That is when x bar k is bigger than 1 by L beta D. Okay, so 1 by L beta D is essentially the threshold. So when x bar k is xdk here, because all nodes have the same degree. Now, when xdk is bigger than the threshold, the activation probability is 0. Otherwise, the activation probability is 1. And this is always true. Now, how does the closed loop dynamics evolve? So there are 3 regimes here. One, when delta is bigger than beta D, then the recovery rate is already high. Then even if all the susceptible nodes are always activating, the xdk decreases. So it decreases all the way to 0. So like the infection goes away on its own, and because the recovery rate is high, not because of what people are doing. The second case is that when the recovery rate is smaller than beta D, in this case, when there was no sort of game theoretic activation, so to speak, what would have happened is that the epidemic should have settled around 1 minus delta by beta D. So xdk should have settled at x star D. This is from the classical SIS epidemic analysis. Now, there are 2 cases here. One is that x star D is below the threshold. In that case, the epidemic settles around X star D. And if X star D is larger than the threshold, then the epidemic does not settle around X star D. It settles around the threshold 1 by L beta D. So if we increase the parameter L, that is if people think that the infection is very, very bad for me, then 1 by L beta T is very, very small. And then the epidemic will settle at at a lower level compared to where it would have settled otherwise. And that is something we see in the numerical results as well. So in the first figure here, so we assume that L equal to 2. So in this case, the threshold 1 by L beta D, denoted by the dotted blue line, is larger than X star D, and the infection settles around X star D. If I increase L, then 1 by L beta D falls below X star D, and in that case, the infection now settles around 1 by L beta D. And this is true for both the exact simulation as well as under the DBMF approximation. Okay, and this is basically the end. So essentially what we try to do is that we studied the evolution of epidemic state and networks under game theoretic decision making. We try to examine the impacts of bounded rationality, asymptomatic carriers, and heterogeneous node degrees. And one of the main insights is that the infection essentially sustains in the population under game theoretic decision making, maybe at a lower level than where it would have, but it sort of doesn't get completely eliminated. And what we are trying to do now is sort of try to learn these parameters, and essentially we're trying to see how to relate these activation probabilities with some sort of like mobility data that Google has made available during the lockdown period. And then we're also trying to sort of combine some type of centralized decision with the decentralized decisions, so to speak. Yeah, any questions? I'm happy to take questions at this point.
Thank you, Professor, for the interesting talk. So if anybody has any question, just unmute yourself and you can directly ask. So yeah. Okay.